Friends, once again welcome. Today we are going to explain the carbon-13 NMR spectroscopy. Also compare with the S1 NMR spectroscopy. Friends, first compare the carbon-12 and carbon-13 nuclei. We know that the natural abundance of carbon-12 is 98.9% and that of carbon-13 is 1.1%. Therefore, natural abundance of carbon-13 is very less as compared to carbon-12. Friends, the spin quantum number that is denoted by I and for carbon-12 nuclei is equal to 0. Therefore, carbon-12 nuclei is a NMR inactive nuclei. But spin quantum number for carbon-13 nuclei is a 1/2. Therefore, carbon-13 nuclei is a NMR active nuclei. That is gives NMR peak, but carbon-12 cannot be gives NMR peak. Friends, then compare the S1 nuclei with the carbon-13 nuclei. The natural abundance of S1 is 99.98%, but that of carbon-13 that is 1.1%. The spin quantum number is same for the both case S1 as well as carbon-13 NMR, but natural abundance is different. Therefore, natural abundance of S1 is more than the carbon-13 NMR. Friends, we know that any charged particle is spin around itself, then it is acts as a magnet, and this magnet have magnetic moment as well as angular moment. The ratio of magnetic moment to that of angular moment is called as gyroscopic ratio. The gyroscopic ratio of S1 is more than the carbon-13. The gyroscopic ratio of S1 nuclei is 267.53 and that of carbon-13 nuclei is 67.28. Therefore, gyroscopic ratio of carbon-13 nuclei is less than S1 nuclei by 4 times. Friends, then chemical shift. The range of the chemical shift in S1 NMR nuclei is 0 to 60 ppm or delta, but that range in the carbon-13 NMR equal to 0 to 220 ppm or delta. Why the range of chemical shift in the carbon-13 nuclei is more? Because the valency of carbon is 4 and valency of the hydrogen is 1. Therefore, 4 times effect are created in terms of carbon-13 as compared to S1 NMR. Hence, there are more variation is observed in the carbon-13 NMR as compared to S1 due to sp, sp2, sp3 hybridization. Hence, the range of the chemical shift of carbon-13 nuclei is more than the S1 NMR. The S1 coupling is observed in the S1 NMR spectroscopy because the natural abundance of the S1 is 99.98%. Therefore, all types of proton are resonated. There are no more number of scanning is required for the determinants of the resonance proton. But in carbon-13 nuclei, in carbon-13 spectra, the carbon-13 coupling is not observed, but carbon-13 S1 coupling is observed. Friends, the carbon-13 coupling is not observed because the natural abundance of carbon-13 is only 1.1%. Therefore, for scanning to determine the resonated carbon-13 nuclei, the probability is very less. Even the probability of adjacent chemically non-equivalent carbon-13 nuclei is even less. Therefore, do not scan the carbon-13 chemically non-equivalent nuclei simultaneously. Hence, the carbon-13 coupling is not observed. But carbon-13 S1 coupling is observed because the spin quantum number of both nuclei are the same and S1 having natural abundance is 99.98%. Therefore, this can easily couple with the carbon-13 nuclei and gives coupling. Then next, hydrogen deuterium coupling is not observed in the S1 NMR spectroscopy because the spin quantum number of hydrogen is 1/2, but the spin quantum number of deuterium is 1. Therefore, shape of the deuterium is ellipsoid. Therefore, their spinning effect, the spinning effect of the deuterium is not an effect on the spin of the S1. Therefore, S1 deuterium coupling is not observed because it is far away. It is attached to, it is not directly attached, but it attached to through 2 or 3 bonds. Hence, such a coupling is not observed. But in case of carbon 13 spectra, the carbon 13 coupling is observed because most of the times the deuterium is direct attached to the carbon 13 nuclei. The spin quantum number is even 1/2 of the carbon 13 nuclei, but deuterium is directly attached. Therefore, one bond coupling is observed in the CMR spectroscopy. Friends, in H-1 spectroscopy, the integration used in interpretation, because what the meaning of integration means, in H1 NMR spectroscopy, the area under the peak gives integration ratio and it is useful to count the number of protons present in the corresponding signal. For example, in this compound there are 3 types of proton. One proton belongs to CH3 groups, other type belongs to CS groups, and third type belongs to CS2 groups. Therefore, in CH3 types, there are 12 number of hydrogen are equivalent. In case of CS, there are 2 hydrogen are equivalent, and in CS2, only 2 hydrogen are equivalent. Therefore, area for CS3 is more. How much? There are present 12 proton. Therefore, 12s2, 2s2, 2s2. That is, integration ratio is 6s2, 6s2, 1s2, 1. Therefore, this ratio is useful to determine the how many number of protons are present in the corresponding signal. Hence, integration ratio is observed because all hydrogen are resonated simultaneously and gives more intense peak. But in case of carbon 13 spectroscopy, the integration is not used for interpretation. Means the number of carbon 13 cannot be counted accurately in the given signal because the natural abundance of the carbon 13 is 1.1%. Therefore, similar types of carbon are not undergo resonated at the same time because the probability of scanning of the carbon 13 is very less. At the same time, all similar types of carbon are not undergo resonated. That is the main reason. Therefore, integration ratio is not useful to determine the number of carbon are present in the given signal. Friends, the carbon 13 nuclei require 6,000 times more magnification than the S1. Means the S1 is more intense peak than the carbon 13 nuclei by 6,000 times. Why? Though we know that again the natural abundance of the carbon 13 is 1.1%, and for S1 the natural abundance is 99.98%. The intensity ratio or intensity depends on the natural abundance. Therefore, intensity ratio of the carbon 13 nuclei to that of S1 nuclei equal to 1.1 upon 99.98. That equal to 1 upon 90. Now, the magnification is also depends on the gyroscopic ratio. Gyroscopic ratio means magnetic moment upon angular moment. Therefore, gyroscopic ratio for carbon 13 is 67.28 to that of S1 to 67.53. Therefore, gyroscopic ratio of the S1 is more than carbon 13 by 4 times. Hence, gyroscopic ratio of carbon 13 to that of S1 NMR equal to 1 by 4. But sensitivity is directly proportional to the gyroscopic ratio to the power 3. Hence, sensitivity that is equal to the ratio of the carbon 13 to that of S1 raised to 3. Hence, 1 by 64. Therefore, sensitivity comparison for carbon 13 to that of S1 is equal to 1 by 64. The magnification is depends on the intensity as well as sensitivity. The intensity ratio is 1 by 90 of carbon 13 to S1 nuclei, and sensitivity ratio is 1 by 64. Therefore 1 by 64 into 1 by 90, that is gives 5760. Hence the S1 is more intense peak, more magnification than the carbon 13 by 5760 times. That means the carbon 13 nuclei require the 5760 times more magnification than the S1, that is approximately considered as 6000 times. Friends, in the CMR spectroscopy, the quaternary carbon gives weak signal. Why quaternary carbon gives weak signal? We know that the natural abundance of carbon 13 is same, that is 1.1%. There is no proton attached on the quaternary carbon. Therefore, their realization time is much more as compared to other carbon which are attached to the hydrogen, that is maybe CS3, CS2, CS. Therefore, realization times of quaternary carbon is more than CS, more than CS2, more than CS3. Therefore, quaternary carbon cannot be obey the perfect Boltzmann distribution law. Therefore, the nuclear also enhancement effect of this CS3 and friends, also nuclear also effect consider. The nuclear also effect for CS3 is more than CS2, is more than CS, is more than quaternary carbon. The nuclear also effect for the quaternary carbon is very weak. Therefore, it can be expand the intensity of the peak. Therefore, quaternary carbon gives weak signal in the CMR spectroscopy. Friends, now discuss the coupling between carbon and deuterium. We know that, consider this compound, the CS2DBr. We know that the spin quantum number of deuterium is 1. In this compound, only one deuterium is present. The number of lines, that is multiplicity, is determined with the help of 2Ni plus 1 formula. N means number of non-equivalent nuclei which can be coupled. Therefore, in this compound, N equal to 1. Therefore, 2Ni plus 1, that is equal to 2 into 1 into the spin quantum number means I for deuterium is 1. Therefore, into 1 plus 1, that is equal to 3. Therefore, this carbon 13, this compound so separate because it is attached to the deuterium in proton noise decoupled spectra. Friends, we know that the number of spin state for deuterium is determined by the simple formula 2i plus 1. Therefore, y means for deuterium equal to 1. Therefore, 2 into 1 plus 1, that is equal to 3. The number of spin state for the deuterium is 3. Means deuterium nuclei are present in the 3 possible spin state, that is equal to maybe plus 1, maybe present in the 0, or maybe present in the minus 1. Now friends, how to determine the intensity ratio for the carbon deuterium coupling? The first, consider the total spin. The total spin, then consider the possible spin state and consider the intensity ratio. In total spin, there are multiplicity is 3. Therefore, there are 3 possible lines are present. The first possible line considered as a 0. The next one considered as a plus 1. And third one is considered as a minus 1. Therefore, in this compound, only one types of deuterium nuclei is present. Therefore, consider only one possible spin state. Therefore, for plus 1, that is considered as only one spin state, that is a plus 1. For 0, the spin state is also 0 for the deuterium because only one nuclei is present in the bracket. For minus 1, that considered as a minus 1 spin state of the deuterium. -1 gives -1, 0 gives 0, +1 gives +1. Therefore, this possible spin state are present only one times for 1, 0, -1. Therefore, intensity ratio for +1 is 1. Intensity ratio for 0 is 1. And for -1 is also 1. Intensity ratio is 1:2, 1:1 for the CS2 dBr. Then consider the next example, that requires deuterated acetone. In this compound, the carbon coupled with deuterium, but there are 3 number of deuterium is present. Therefore, value of I for deuterium is 1, but N equal to 3. Therefore, multiplicity, that is number of lines, equal to 2Ni plus 1. Therefore, 2 into 3 into 1 plus 1, that is gives 7 lines. Hence, in the proton noise decoupled spectra of the deuterated solvent use 7 line because they couple with the deuterium. We know that the possible spin state of the deuterium is 2I plus 1, that is 3. One is plus 1, other is 0, and third one is minus 1. Now friends, there are 7 lines are obtained. Therefore, consider the first line, total spin equal to 0. The second line, that is considered as a plus 1, third line considered as a plus 2, and fourth line considered as a plus 3. Similarly, minus 1, minus 2, minus 3. There are 7 lines are present in the total spin form in this way. Now, how to determine the possible spin state? In this compound, 3 number of nuclei, 3 number of deuterium nuclei attached to the carbon, coupled to the carbon. Therefore, in the bracket, consider 3 spin for plus 3. Therefore, consider the plus 1, plus 1, plus 1. The plus 1, plus 1, plus 1 gives plus 3. This possibility is only 1 times. Now, plus 2, that is gives possible spin state is 1 plus 1, 2 plus 0, 2. Therefore, this is gives plus 2. Or in second bracket, consider the first plus 1, the second nuclei having spin 0, third nuclei having spin plus 1. Or this is also possible, the first nuclei having spin 0, second one is plus 1, and third one is also plus 1. Therefore, 1 plus 1 plus 2, 1 plus 0 plus 1 plus 2, 0 plus 1 plus 1 plus 2. Therefore, there are 3 possibilities. Now, how many possibilities in case of total spin is plus 1? Now, consider the 0, 0 and plus 1. The second possibility is 0, 1, 0. The third possibility is 1, 0, 0. The fourth possibility is 1 plus 1, that is 2, minus 1, that is plus 1. Therefore, plus 1, minus 1, plus 1, that is also gives plus 1, total spin plus 1. Minus 1, plus 1, plus 1, that is total spin is also plus 1. Therefore, there are 6 possibilities. Now, how many possibilities when total spin state is 0? We know that in this compound, the 3 deuterium is attached. Therefore, consider 3 spin in the bracket. The first spin of the first nucleus, that is 0. The spin of the second nucleus is also 0. Spin of the third nucleus is also 0. Therefore, all sum gives 0. Now, second way in which the first nucleus having spin 0, the second nucleus having spin plus 1, and third nucleus having spin minus 1. Therefore, 0 plus 1 minus 1, that is also 0. Third one is 0 minus 1, 1. Then minus 1, 1, 0. 1 minus 1, 0. That is also 0. 1, 0 minus 1. Minus 1, 0, 1. That is 7 times possibility. And similar, minus 1 gives like plus 1. Only 1 replaced by minus 1 and minus 1 replaced by 1. Similar that of minus 2 and minus 3. Therefore, intensity ratio for total spin is plus 3 is 1. For plus 2 is 3. For plus 1 is 6. For 0 is 7. For minus 1 is 6. Minus 2 is 3. And minus 3 is 1. Intensity ratio for this 7 line is 1:2, 3:2, 6:2, 7:2, 6:2, 3:1. In H1 NMR spectroscopy, the intensity ratio are easily calculated by using Pascal triangle. But in this case, the intensity ratio are calculated like this way. Now, the next point, that is called types of carbon-13 spectra. the first types of carbon-13 spectra, that requires proton coupled spectrum. In this spectrum, the proton coupled with carbon through one bond, through two bond or three bond, sometimes four bond coupling is also observed. Therefore, it is a more complex spectra and it is not useful spectra because the accurate information of chemical shift and multiplicity are not obtained from that spectra. Therefore, such spectra are not important as a point of determination of the structure of the carbon-13 on the basis of carbon-13 NMR. Now, the second spectra, that requires proton decoupled spectra, or this is also called proton noise decoupled spectra. In this case, the all carbon signal shown singlet only when this is not attached to the deuterium. If this is attached to the deuterium, therefore this gives multiplicity. But this is attached to the hydrogen or not attached to the hydrogen, that is all carbon-13 signal having singlet. Therefore, it is useful spectra because the accurate chemical shift information is obtained, but multiplicity information is lost. Such spectra are obtained by irradiating all types of proton by one channel at a saturated state and take the carbon-13 spectra by second channel. It is useful because accurate chemical shift information obtained but not the multiplicity information obtained. Therefore, the third spectra, that requires off resonance spectra. In this spectra, the multiplicity information as well as the chemical shift information is obtained in more accurate way. First, how to take the off resonance spectra. The first, all types of proton are irradiated by one channel at a saturated state and carbon-13 are resonated by second channel and measure the frequency of the carbon-13 resonated nuclei by the second channel. But at the same time of the first channel and record the spectra within a fraction of time. Therefore, one bond coupling is observed, but two bond, three bond coupling is not observed in this spectra. Therefore, this spectra gives more accurate information of multiplicity as well as chemical shift information. Now friends, the next technique, that is called as distortionless enhancement polarization transfer. Such a technique are more useful to distinguish the CS3, CS2, CS carbon. Friends, it is useful for, that is, distinguish between the primary, secondary or tertiary carbon by applying the different types of pulse. We know that how to apply the pulse. We have already focused in the some previous video. Now, the signal from quaternary carbon or other carbon which are not attached to any types of hydrogen directly cannot be recorded in the DEPT. Friends, there are three types of DEPT generally considered: DEPT 45, DEPT 135 and DEPT 90. The first, in Proton Noise Decoupled Spectra, the all signal are obtained in this spectra, one signal for CS3, one for CS2, one for CS and one for the quaternary carbon. But in DEPT 45, only those carbon use signal which are attached to the hydrogen, but which are not attached to the hydrogen cannot be used the signal. The signal for CS, CS2 and CS3 are obtained in the positive deviation. But in case of DEPT 135, there are two types of deviation considered. The upward gives positive deviation and downward signal gives negative deviation. The signal for CS and CS3 are obtained in the positive deviation. The signal for CS2 gives in the negative deviation. Now, in DEPT 90, only CS peak is obtained in the positive deviation. Therefore, DEPT 90 is more useful to distinguish between the or to determine the either peak are CS3 or CS as compared to DEPT 135. And DEPT 135 is also useful because it is easily give the peak of the CS2 in the negative deviation. Therefore, as a comparison between these three depth, the depth 90 and depth 135 are the most useful for determination of the structure on the basis of carbon 13. I hope that, friends, some concepts are clear on in the carbon 13 as well as H-NMR spectroscopy. In the next video, I will focus on the chemical shift on carbon 13 with compare the H-NMR chemical shift and some their factors. Thank you so much and take care.